Okay, so today I want to prove the localization formula for a circle action of Atiyah-Bott and Berlin-Vernier. Okay. Now, last time I introduced the real blow-up. Okay. So let's review that. Okay. So if sigma from m tilde to m is the real blow-up of m at a point P in M. So that has a picture like this. Outside of P, sigma is a diffeomorphism, but P, the inverse image of P is a sphere. Okay. And locally, relative to a chart at P, so sigma is given by okay, so sigma goes from U tilde to U is given by, okay, you define U tilde to be the set of pairs XV in U cross Sn minus 1. So Sn minus 1, it's all the tangent directions at P. Okay? And X is T of V for some T. Now, if X is not 0, then X is a multiple and okay, so V is a unit vector for some T in R, and V in Sn minus 1 is unit vector. Okay? T should be positive, greater than or equal to 0. Okay? So if X is not 0, then X is equal to, it's norm times X over its norm, right? And for a unique T. Oh, and I should say that sigma takes xv to x. So if x is not 0, then it has a unique inverse image. X over normal X. But if X is 0, then the inverse image is the whole sphere, then the inverse image of x, okay, the inverse image of 0 is 0v. Okay, for all v in Sn minus 1. Yeah. Okay. So sigma, it blows down the sphere to a single point, and it's a diffeomorphism elsewhere. And we call it the blow up of M. Okay, now if F is a C infinity map with P as a fixed point, then it induces a map upstairs outside of P, you have a diffeomorphism, so it's the same map. Okay, so outside on M tilde minus the inverse image of P, sigma is a diffeomorphism. So you can define F tilde to be, you first map down by sigma, then you map by F, and then you map by sigma inverse. Okay? And then, okay, and then on sigma inverse of P, which is a sphere, and that, that sphere, it's really all the tangent directions at P. So you have that sphere, and you want to define F at a point V of the sphere, okay? But that sphere maps to the point P, and the V is a tangent direction. And now, take a curve with that V as the direction. Now that curve corresponds to a unique curve upstairs. And we have already defined the values on that curve. It's these values, okay? And so the value at V, it should be the differential. So F tilde at V, and V is a tangent direction at P. It should be the differential, okay? But you want it to go into the unit sphere itself, so you need to divide by the norm. So on the sphere, by continuity, you define F tilde by continuity, and it has to be defined this way. Yeah. Now, okay. Okay, so now let's consider an action of S1 on M. Okay. So suppose S1 acts on M. Because S1 is compact, you can put the invariant metric. So on M, put an S1 invariant metric on M. Then S1 acts by isometries. Okay, so because it preserves a metric, and at a fixed point P, so the tangent space is a representation of S1. And so S1, so it decomposes into a direct sum of irreducible representations. Okay. And you know that when you have only isolated fixed point, this S1 acts on M with isolated fixed points, then in that case, the dimension of M is even, so 2n. And when you decompose it into irreducible representations, you don't have a trivial summand, so you get this, okay? Where mi are non-zero. And L is the standard representation of S1 on R2. Okay. Yeah. Now, so the action of S1 on M induces an action on the blow up. On M tilde. That takes the sphere. Let's see. Let's call this the inverse. Yeah, the inverse image of P is a sphere. Okay. And I'll put the P there because it's the inverse image of P. Okay. But now here N is the so here N is the dimension of M, right? But now the dimension is 2n, so the sphere is 2n minus 1. Okay. And this action will take the sphere to the sphere, because everything else is the same. And then the sphere, it's the tangent directions. And the sphere is it's the sphere in the tangent plane. Okay. Okay. Now, so if so an element of the tangent plane is a vector with 2n coordinates. So I'm going to write it as u1 v1 to un vn. Okay. So if w is in there, then a point of the sphere, a point of the circle, e to the it, act on w as the direct sum of these representations, and each one of them is a multiple of a rotation. L is the standard representation. It's the standard representation is e to the it dot xy is equal to cosine t sine t minus sine t cos t times xy, right? That's the standard representation, okay? And if you raise it to the power m1, then it's going to be, okay, so I'm going to introduce a shorthand. This is, I'll call this the rotation matrix through angle t. Okay? And so this will be the rotation through m1t, rotation through mnt. Okay, it will be a 2n by 2n matrix times u1 v1 un vn. Okay. Now let's write down the formula for the fundamental vector field and for the invariant form theta. Okay. So to write down the formula for the fundamental vector field, I have to choose some x in the Lie algebra of the circle. I'm going to choose this one, minus 2 pi I. Okay, so there's a minus sign so that it will cancel out the minus sign in the fundamental vector field. So this is an element of the Lie algebra of the circle. Okay. Then the formula for the fundamental vector field at W, it's ddt at t equal to 0 of e to the minus xt, that will become 2 pi it dot w. Okay? And so this will be ddt t equal to 0 of this matrix, the rotation matrix of, now there's an extra 2 pi m1t, 2 pi mnt times w. Okay. Now when you differentiate the rotation matrix, let's see, cosine becomes sine. So at 0 it will be 0. And then sine will become cosine with a factor of 2 pi m1. And cosine is 0, is 1. So you get 2 pi m1. And then this will give you minus 2 pi m1, 0. Okay? So that's a derivative. And here you will have 0, 2 pi mn minus 2 pi mn 0 times U1 V1 UN Vn. Okay?
Excuse me. So now this fundamental vector field should be living in the tangent space of the tangent space of n.
Let's see, it is
W is vector.
this fundamental vector field. It's in the, yeah, it's, oops, sorry, oh God. Is it still working? Yeah. Okay, it's a vector field on the tangent space. Because now we're looking at we're looking at the action of the circle on the tangent space. So this is a fundamental vector field. So x bar is a vector field on the tangent space. Okay? Mm-hmm. And it's given by this formula. Okay, if you write it out, then it's minus 2 pi m1 times v1. That's the first coordinate. The second coordinate is 2 pi m1 times u1. Okay? So let's see. So the formula, when you multiply it out, is this. It's going to be minus 2 pi m1 v1, 2 pi m1 u1, minus 2 pi m1 vn, 2 mn, minus 2 pi mn un. Okay. Multiply out, it's this. And this is a vector field. So it is the sum. First of all, you can take out the 2 pi. And then the sum over j from 1 to n of vj dvuj plus minus vj dvuj plus uj dvvj. Okay, so it's this vector field on the tangent space. Mm-hmm. Now, a one-form theta on the tangent space such that theta of x bar is 1 is, so theta is equal to 1 over 2 pi. Oh, just a minute, I left out the MJs. There should be an MJ here. Okay. Okay, so the one form that when applied to x bar will give you 1 would be, now I have to have 1 over 2 pi and then 1 over mj. Okay, and then I have minus vj duj. Okay, that's going to give me vj squared plus uj dvj. Okay, so if I apply this to this, I'm going to get uj squared plus vj squared and so I need to, in the end, if I apply this to that, I'm going to get the sum of uj squared vj squared. So I need to divide by the sum of uj squared plus vj squared. Okay. Then this will give me 1 when I apply it to x bar. Okay? All right, good. And now, we're going to just restrict the action to this sphere. Okay. So the fundamental vector field will be defined only on the sphere. So on SP2n minus 1, x bar is given by the same formula. Okay. 2 pi. I don't need the W. Okay, and then theta on the sphere, this sum is 1. So you get 1 over 2 pi, 1 over nj, minus vj, duj plus uj, dvj. Okay? Now, we need this. We need this formula because we have to write out the formula for the homotopy, cochain homotopy K, right, which was defined in terms of theta. Okay, now, there are a few things from differential geometry we need. The first is the volume form, the formula for the volume form on a sphere. Okay. So now the sphere Sm minus 1, it's in Rn. This is the unisphere. And it is the boundary of the ball. Dn. Now Dn is a subset of Rn. So Dn has Dn, can be given the same orientation as Rn. Which is so the volume form of Dn is dx1 wedge dxn. Okay? And then we give Sm minus 1 the boundary orientation of Dn. So it becomes oriented, and then its volume form is equal to, the boundary orientation is the one where you have an outward vector. So the radial vector is R, which is the sum of xi ddxi. Okay, that's the radial vector. And then the volume form on Sn-1 is an n-1 form. Do you know the formula for the volume form of the boundary? Yeah, you just contract the volume of the manifold with an outward normal vector, okay, of unit length. So it's this. The volume form on the sphere is given by this. I will send you a chapter on volumes in differential geometry, and it will have this in it, okay? So we need to calculate I of the sum of xi ddxi with dx1 wedge dxn. Okay? We need to calculate that. Okay, now, and that's easy to calculate because ddxi is going to give you 0 when you apply to these dx1 and so on, except dxi. So dxi is going to give you 1, and you have to go across I minus 1 of the 1 form. So it will be minus 1 to the I minus 1 xi. Okay, dx1 wedge. Now dxi will disappear because it will give you a 1. Okay? So this is the formula for the volume form on the n-1 sphere. And then you want to calculate the surface area of a sphere, and the formula is different depending on whether it's an even sphere or an odd sphere. Okay, and we just need the formula for an odd sphere. So now the surface area, well, that's the volume of the sphere. So you get that by integrating the volume form. Okay, so you have to integrate this on the sphere. And you know, that integral is easy to do if you use spherical coordinates. So you can convert that formula to spherical coordinates, and then you can carry out the integration. Okay? So this is something that's done in differential geometry. And yeah, so I will give you the, that chapter on differential geometry, and you find that the formula is 2 pi to the n over n-1 factorial. Okay? So that's the formula for the surface area of an odd sphere. You see, if n is equal to 1, then you just get 2 pi, which is the circumference of a unit circle. Okay? Okay, so we will need this. You see, in the localization formula, we convert the integral into an integral over spheres. Okay? And so if we can integrate over spheres, then we'll have the formula. Okay, so now let's prove the localization formula. Okay, so suppose S1 acts on M with isolated fixed point set F. And the first thing that we do is we blow up the fixed points. So we blow up the fixed points. That means we replace each point by a sphere, by a unit sphere of all the tangent directions at P. Okay? So let sigma be the blow up at all the fixed points. And then we choose X, a non-zero element in the Lie algebra of S1. Okay. Now, then there's a Cartan differential up here, upstairs, and the Cartan differential downstairs. So I claim that dx sigma star, if you pull something upstairs and then apply the Cartan differential, is the same as taking the Cartan differential and then pull it upstairs. Okay? So on the Cartan complex, yeah, so we want to integrate an equivariant differential form. So phi is in the Cartan complex. Okay. All right. So let's see. Let's prove this lemma. So dx sigma star of phi. Now this is so this by definition is d sigma star phi minus u ix sigma star phi. Okay. Now d in the pullback commute, so this is sigma star d phi. Okay. Minus u ix sigma star phi. So I have to see if ix and sigma star commute. Now, Ix sigma star phi. Okay, so this will be a polynomial in U with coefficients in the forms. And so I apply it to some vectors. And then by the definition of Ix is sigma star phi. And then I put that x in the first argument, and it's upstairs. So it's the fundamental vector field on M tilde. Okay? And then the rest of them. And by the definition of pullback, this is phi, sigma lower star of x bar tilde, and tilde, sigma star applied to these arguments. Okay? Now, you have a fundamental vector field upstairs and a fundamental vector field downstairs. Now, outside the fixed point, it's a diffeomorphism. So the fundamental vector field upstairs will go to the fundamental vector field downstairs, outside the fixed point. Okay? Now, at the fixed point, what happens? I mean, what happens to this vector? Under the differential? It goes to zero, right? Because it's tangent to this sphere, to some curve on the sphere, and that curve goes to a constant, a point. So the tangent will go to the tangent of the point, so it's zero. Okay? So this will go to zero at P, but that's precisely the fundamental vector field at P. At a fixed point, the fundamental vector field is zero. So this fundamental vector field upstairs will map down to the fundamental vector field downstairs. Okay? And this is Ix phi, sigma star. And that's sigma upper star Ix phi. Yeah, so we see that Ix and sigma star commute. Okay? So therefore, dx sigma star phi is equal to sigma star d phi minus u sigma star Ix phi. Okay. And sigma star, yeah, that's, it doesn't do anything to u. So you can bring the u inside, and so you get sigma star dx phi. Okay? So that proves the lemma. Sigma star and dx commute. Okay. And now we want this phi to be equivariantly closed. Now we have found a Cauchy homotopy K on the localized Cartan model such that So K is given by multiplication by an element alpha, right? And that alpha, if you remember the formula for alpha, So who remembers the formula for alpha? Yeah, yes. Yeah, minus theta over u times. Yeah, e theta over u to the n minus 1. Okay, so that's the formula for alpha, and so the formula for k is this. And then we show that it's a cochain homotopy, so it satisfies this. dxk plus k dx is the identity. Okay. So if you apply it to an equivariantly closed form phi, you get dxk phi, and then here k dx phi will be 0. So that will be equal to phi. Okay. So we have written phi as dx of something. Okay. And yeah, so that's the key step. M is of dimension 2n. Yeah. So here, yeah, that's right. M is so dimension of M is 2n. And this has degree 2n minus 2, right? Because d theta has degree 2. Yeah. If you just look at d theta, it has degree 2. So d theta to the n minus 1 has degree 2n minus 2. And then you multiply by theta. So the form has degree 2n minus 1. Okay? But then you are actually dividing by these u's. So these guys actually has degree 0. Theta has degree 1, u has degree 2, so alpha has degree minus 1. Okay? And that's the way it's supposed to be, because k is supposed to lower the degree by 1. Mm-hmm. I think I'm going to leave the formula for the volume of the sphere there. Okay. Okay, and now I want to calculate the integral of phi over n. And I can remove the fixed point set and get the same integral because the fixed point set has measure 0. It's a set of isolated points. Okay. Now, if I remove the fixed point set, then it's diffeomorphic to the blow up minus the boundary of the blow up, which are a union of spheres. So I can do my integration upstairs. Okay? So because sigma from the complement of the boundary to n minus f is a diffeomorphism Mm-hmm.
Is that M tilde minus boundary M tilde?
Oh, M tilde, yeah. Minus the boundary of M tilde. Right. Uh-huh. Now, this sigma star of phi is equivariantly closed because dx of sigma star of phi is sigma star dx phi, so it's 0. Okay? So it's equivariantly closed. If it's equivariantly closed, then you can write it as yeah, so I want this to be upstairs. Okay, let's do it upstairs. Mm-hmm. And so I can write this as dxk sigma star phi. No, before I do that, let's see. Before I do that, I can say that this integral is the same as the integral over M tilde because the boundary has measure 0. Mm-hmm. And okay, and then let's go over here. Okay, and then oh gosh, yeah, okay. I think I should stop. So let's stop and take a break for 10 minutes. Okay, because you'll take another 10 minutes to finish this. Yeah, and.